or look at more examples of how we can use cofunctions. And so the previous example, number 5, which we did in class, where we were looking at specific things about 18 degrees. We knew exactly where 18 degrees lived in quadrant 1, and we there was no ambiguity of other possible triangles or angles that we would be evaluating. Okay, and so I want to contrast that with what I'm going to do with example number 3, where they don't really tell us exactly how big theta is, but we just know its cosine value is 3/5. Now, I hope you do recognize that 3/5 is a nice cosine ratio, because what it allows us to do, or I mean, like it reminds us that it's a 3-4-5 triangle. So cosine is 3/5. So the adjacent is 3. Hypotenuse is 5, which means our missing side is 4. So my reference angle that I draw here is theta. That's one place where cosine could equal 3/5. What I have to also remember is that theta could be drawn in the fourth quadrant, because cosine's also positive down here, right? So where this hypotenuse is 5, I'm trying to grab that 3 out of the way there. Oh, and you can't really move it. That's okay. But then the other leg is 4, but it's 4 below, so we know that's really like -4. So there are actually two possible thetas that we can be given, that each have a cosine of 3/5. So when we start to evaluate the different problems below, we'll have to consider both triangles, like like both possible locations. When we just had like 18 degrees, we knew it was just 18. Like there was no other quadrant, because we had a very specific concrete value. Okay, so we'll always have to reference those two thetas. So the procedure is to try to simplify this expression so it's just a theta. And so the first one, sine of 90 minus theta, might be the most direct, because I know that as a cofunction, I could rewrite that as theta. So even though I don't have like the 18 degrees, 72 degree pairing that I know adds up to 90, I know that those are expressions that, if I highlight those, that like 90 minus theta versus theta, I know those are complementary. I know that their cofunctions would be the same. Okay, so cosine of theta. So I have to look at both triangles, but in both triangles, cosine of theta is 3/5. So I just get one answer. It's just 3/5. Okay, so how about cosine of 90 minus theta? Well, again, this expression 90 minus theta, we should recognize as complementary to theta, so we can rewrite that as sine of theta. So again, thinking about like procedures, we want to write our angle as an acute value theta. So we want to write our angle as theta. And that theta could be representing in quadrant 1 or 4, but as long as we write it as theta, that's like sort of like step 1. And so then what is the sine of theta? Well, in one particular triangle, okay, so highlighter here. So like the sine of theta would be 4 to 5. But in the other triangle, the sine ratio is -4 to 5. Since I'm considering both thetas, I would have to give both answers. So I say plus or minus 4/5. So 10, so that equals plus or minus 4/5. So some of these problems, again, because I have two triangles, I might get a plus or a minus. Okay, let's look at the next one then, part C. So part C, hopefully you're okay with that. Pi over 2 minus theta is the same thing as 90 if it was in a degree mode. So I could rewrite this as its cofunction secant of theta. And once I have theta, I look in both quadrants. So right angle is theta. We want to look in both quadrants. Now, in this particular case, I know the secant of theta is going to be the same value, 5/3, 5/3. So in this case, it's just 5/3. Okay. Next one, secant of theta. Well, that's kind of redundant. I'm not even sure why I gave that one. Sorry. We just did it. So that's a freebie. That's so nice. Okay. Let's look at hopefully a different one. So secant of 90 minus theta. Okay, so that's the same thing as cosecant of theta because of the cofunction. Now, again, looking at both triangles, so cosecant in the one that's in blue is 5 to 4. The one in green was 5 to negative 4. So we would have to report it as plus or minus 5/4. Okay, cotangent of theta, it's already written in theta, so we look at both triangles. It's either 3/4 or negative 3/4, so we say it's plus or minus 3/4. Okay, so now maybe a little more complicated. What if it doesn't look like 90 minus theta? What if it looks like example G, 180 minus theta? So in that case, I suggest to draw out what that kind of looks like so we can write it in terms of theta. So if you drew 180 degrees, but then you backtracked theta, your angle then, oops, I'm sorry. Your angle would be right here. So that red angle, this right here would be 180 minus theta, which means that theta on the outside is our reference, right? That is our reference angle. So our reference angle is theta. So I can rewrite that as an expression that's just theta. But remember, I have to describe the behavior of this particular theta for this particular problem in quadrant 2. And when I'm sitting over here in quadrant 2, I know that tangent is negative. So I'm looking to write an expression of negative tangent of theta. So now I go back up to my picture, and tangent of theta in this upper quadrant is 4/3, and this lower quadrant is negative 4/3. So I have negative plus or minus 4/3. Negative plus or minus 4/3. Now, the opposite of plus or minus 4/3 technically is still plus or minus 4/3. But I sometimes like to flip it to make it a minus plus 4/3, right? So you can be cool like me. But the minus plus 4/3 indicates that there was an order change. And in this case, it doesn't matter because listing them out, order is not going to matter. But we will find this semester that sometimes like listing negative and then positive is a big difference compared to listing first positive, then negative. And so I think maybe a third step up here as I'm kind of keeping track is look at both quadrants. And then also we would say account for the behavior, the plus minus behavior of the function for angles greater than 90 degrees. Okay, and speaking of that, that's exactly what our last one on this example is, 90 plus theta. If you were to draw what this particular problem looked like, you would have 90 degrees and theta more. So we are an angle that's bigger than 90 degrees. So I'm going to have to think about that last step. So I'm looking at this angle here, 90 plus theta. And in this case, 90 plus theta, I need to know what is this angle right there to use as a reference. And so again, if the outside is 90 plus theta, that means that this angle right there would be 90 minus theta as its reference. And if you're wondering, how did you know that? I don't know if I'd be able to get that. Well, we know that like this is a straight line adds up to 180. And so if we knew that this was 90 plus theta on the outside, we could say, well, what's left over is 180 minus 90 plus theta. And that's how I would get 90, distribute the negative minus theta. So I know the reference angle is 90 minus theta. So I know that this could be written as its acute representation, which is 90 minus theta, and it's the sine function. So then we've got to remember, what is the behavior? Oops, not the crayon, sorry. What's the behavior of sine in quadrant number 2? Well, it depends on the y value. And in quadrant 2, the y value is positive. So since this is a positive value, I know that this is just a positive value here. Or at least I shouldn't say, at least I should say we don't have to account for its negative. I'm looking for something that's sine of 90 minus theta. And then, okay, well, what's the sine of 90 minus theta? Cosine theta. And I go back up to my picture and look at both quadrants. The upper quadrant, cosine is 3/5. The lower one is 3/5. So in this case, I just get one answer, 3/5. Okay, so I'm going to pause this. Well, actually, I'm going to stop this video, and then I'm going to redo example 4. And so certainly I would suggest maybe try number 4 before you watch me do it, and then go through the video, and then check your work.